At the end of the last video, we'd obtained values for the conditions behind the first shock wave, so we're calling those conditions 2. We determined those by first of all finding the shock wave angle beta and then finding the Mach number component normal to the shock wave upstream of the shock, Mn1, and using that to determine all how conditions changed across the shock. What we're going to do now is look at an alternative way of calculating those conditions. I'll just slide the screen down. And the alternative is to use a compressible flow calculator. So we'll use that for shock S1. And just a reminder that upstream of the shock, the input Mach number is M1 is equal to 6.8, and the flow turning angle, and we are going to be looking at the weak shock solution, is θ1 is equal to 8 degrees. So we'll use the compressible aerodynamics calculator, the one by William Davenport from Virginia Tech. There's a link to this from the course material. I'll move that screen down because we're interested in the oblique shock relations. So we want to put in our Mach number is 6.8. We've got a weak shock and our turning angle is 8 degrees, and then we'll calculate for that. Now I've just blown that up a bit more so that we can see it more clearly, and we can see here that this gives us the Mach number downstream of the shock wave. It gives us the shock wave angle, 14.68 degrees, gives us the ratio of static pressure, static density, static temperature, and how much the stagnation pressure changes across the shock. Also gives us the normal components of the Mach number upstream and downstream of the shock. So let's use these numbers here to check our conditions for the flow downstream of that first shock wave. So let's just look at some results from that. The compressible aerodynamic calculator gave us that the wave angle, and we're calling that beta 1, is equal to 14.68 degrees, and we'd read off 14.7 degrees from the chart. Now this calculator gives us quite precise numbers, so what I'm going to do is I'm going to work to 4 significant figures as we go through this calculation. I'm going to do that because any rounding errors can cascade as we go from across the first shock to the second shock to the third shock. So it's worthwhile keeping our significant figures, even if we're not going to use them at the end. The calculator also gave us directly the Mach number downstream of the shock wave, and that was 5.453 compared with 5.43 that we'd calculated from our earlier analysis. The calculator gave us the change in static pressure across the shock as being 3.299, so we can use that to calculate the static pressure downstream of the shock, and since P1 was 1 kilopascal, it means that the static pressure downstream of the shock is 3.299 kilopascals. And that compares with our value of 3.31 that we'd calculated up here. The calculator gave us the static density ratio being 2.236, so therefore our static density downstream of the shock comes out to be 0.03542 kilograms per meter cubed, and that compares with our value of 0.0355 that we had above. The calculator also gave us the ratio of static temperatures across the shock being 1.475, and we can use that to calculate T2 is equal to 324.6 Kelvin. And we compare that with our value of 325 Kelvin that we got up here. Now there's one more piece of information that I want to extract from this aerodynamics calculator, and that's how the stagnation pressure changes across this shock wave. The calculator gave us that P02 over P01 is 0.8458, so we can use that to calculate that the stagnation pressure, P02 downstream of the shock wave, is 2.914 megapascals. And that was obtained after noting that the stagnation pressure upstream of the shock of the oncoming flow is 3.445 megapascals. Now we didn't calculate that in our analysis above. We could have done, we've got the equations to do it, but I was a little bit lazy, so we've got that out of the calculator. So you can see that things can be a little bit quicker with the aerodynamics calculator, but we get the same results, maybe with a slight difference in the down at the third significant figure. So we can now move on to look at what happens across the second shock wave. I'll just slide the screen down. So we want to look at shock wave S2, and the conditions for the flow upstream of that shock are going to be the conditions that we've just obtained for the flow downstream of the first shock wave. So therefore our input Mach number is going to be, and this is now M2's the Mach number upstream of the shock wave for this second shock, so that's 5.453 from up here. Our turning angle is again the weak shock solution, and now we've got θ2, and we said that the second surface deflects the flow through an additional 10 degrees. So we'll bring back up our aerodynamic calculator. And now the Mach number of the flow upstream of the second shock wave is going to be the Mach number downstream of the first. So we can just insert that here. Our turning angle, we've said, is going to be 10 degrees. So we can calculate what happens across the second shock. So this shows us that the Mach number is now dropped down to 4.3, just above 4.3. The wave angle is about 18.5 degrees, and we've got the static pressure ratio, static density ratio, static temperature ratio, and this ratio of the stagnation pressures across this shock wave. So we can take this information back and use it in our calculations. So we get that the shockwave angle beta2 is 18.47 degrees, and the Mach number downstream of the shock, which in our current notation is going to be M3, and that was 4.301. The ratio of static pressures across the shockwave is 3.315, so that's going to be P3 over P2. So we can use that to find our value of P3. Knowing our value of P2 from above, and that gives us that P3 is 10.94 kilopascals. The ratio of the static density, which will be rho 3 over rho 2, is 2.243. So we use that with our rho 2 from up above here to find that rho 3 is equal to 0.07944 kilograms per meter cubed. The static temperature ratio across the shock is 1.478. So we find that that will give us our T3 is 1.478 times T2, which was 324.6, giving us 479.8 Kelvin. And finally, across this shock wave, the ratio of stagnation pressures is 0.8442. So that's going to give us that the stagnation pressure downstream of this shock wave is 2.460 megapascals. So we're starting to lose that total pressure as we go across these shock waves. I'll move the screen down and we'll see what happens across the third shockwave, S3. So the Mach number upstream of the third shockwave is going to be the Mach number downstream of the second. So that's our M3, and we said up here that was 4.301. And our flow turning angle, and again weak shock solution, in this case is going to be the theta deflection, so we could call it theta 3, but we won't. We'll say it's theta 1 plus theta 2, so that's equal to 8 degrees plus 10 degrees, so that's 18 degrees. So we went through that, why that's the case. We need to go back through that turning angle to bring the flow back parallel to the oncoming flow. So back to our flow calculator, and we can pick up the Mach number downstream of the second shock, so upstream of the third, put it in here. Our turning angle we've said is 8 degrees plus 10 degrees, so 18 degrees, and then we can calculate what happens across this shock wave. So we find that the Mach number downstream of this shock wave is now down to 2.874. We've got a wave angle of 29.3 degrees, and there's our static pressure, static temperature, and static density ratios, and also how much total pressure we're losing. And it looks like we're losing a lot now. We're up to 67% is all we get through this shock wave. So we'll go back and put this information now into our calculations. So we can put in directly our shockwave angle, 29.26 degrees, and the Mach number downstream of the shock, which is going to be our M4, is 2.874. So the ratio of static pressures gives us what P4 is going to be downstream of the shockwave. The ratio of static densities leads us to rho 4, 0.2236 kilograms per meter cubed. The ratio of static temperatures gives us that T4 is now up to 850.2 Kelvin, so getting nice and hot. And finally, we get the P04 over P03 gives us that P04 is down to 1.656 megapascals. Just slide the screen down. And let's now summarize the results by looking at the performance of this as an intake. So let's look at the overall compression of this intake, and we'll look at that in terms of a few parameters. Let's look at the area contraction first, and I'll look at that in terms of the initial area to the final area. And since this is a two-dimensional inlet, we can just take the height of capture over the height at the end, and so that's 1 meter capture height and 0.0853 meters at the entry to the combustor, which gives us that we're contracting the area by a factor of 11.7. Let's look at what our pressure ratio is. So we'll look at that in terms of the static pressure that we end up with, so P4 over the static pressure that we started with, P1. So we ended up with 54.6 kilopascals in the combustor, and we started off with 1 kilopascal upstream of the oncoming flow, so that gives us a pressure ratio of 54.6. We'll look at our temperature ratio, so T4 over T1, and we got to 850 degrees Kelvin in the combustor, and we started off with 220 Kelvin, so that gives us temperature ratio of 3.86. And let's finish up by looking at how much stagnation pressure we lose across this inlet. So we'll look at the ratio of P04 over P01. We ended up with 1.66 megapascals at entry to a combustor. we started off with 3.45 megapascals. So what that means is that we lose, or we only pass, about 48% of the stagnation pressure from our intake to our combustor. And that brings us to the end of our analysis of this problem. So we've calculated the states of the gas at all points through the inlet and into the entry of the combustor. And we've also looked at the overall performance of this inlet. And it's not a great inlet. We only get 48% of the stagnation pressure into the combustor that we had at inlet to the engine. So it's a pretty lossy engine, inlet for this engine.